base k numbers, this type of problem is quite common in AMC10. Now, we start with base 10. If we have the digit ABCD, where the digits is going to be 0 to 9, the value is actually D means the singles, C is counting tens, B hundreds, A would be thousands. So in other words, it's actually A times 10 to the third power, 10 to the second power, 10, and then 10 to the zeroth power, which is the singles, right? So that's good to know. Now, in the base other than 10, for example, base 7, where we only have digit 0 to 6, and this number would apply similar rule. This is going to be singles, this is going to be sevens, this is going to be counting 7 squared, which is 49, this is going to be 7 to the third power. So in this case, the actual value converted into decimal or base 10 is going to be 5 times 7 to the third, 7 to the second, 7, and then singles. Alright, that's good to know. So a lot of times this kind of problem is related to the modulus arithmetics. So kind of quick recap on that. Now, if we consider mod 13, we said that two numbers are congruent if when dividing by 13 they have the same remainder, right? So A and B are congruent with regard to n if the remainder when divided by n are the same. In this case, if the difference here is going to be multiple of 13. So in other words, when two numbers are congruent, the remainder is the same, or the difference is a multiple of that number, right? So here, the congruence, and then the difference would be 26, which is twice of 13, is an integer multiple of 13. So that's good to know, right? And another thing that another time when we calculate the modulus, right, you can actually calculate the modulus first, and then make the multiplication of the numbers. And also, if two numbers are congruent, and you can have the multiplication of that, or two numbers are congruent, you can raise to the same power. In this case, possible integers, when you raise to the same power, they are also congruent with regard to modulo n. So it's very common in number theory and in base 10 numbers. Now, for example, if we have this number n, what is modulus of 6? Now, you don't have to do the multiplication first. You can calculate the modulus first and then do the multiplication later. So what you do is you calculate individual ones, right? So that's the value here is going to be 3. Okay? So here, when you try to calculate modulo 9 of this number, this is actually 772. Notice that individual terms here, 110, when you do mod 9, is always remainder of 1. So here n congruent to 3 times 1 plus 7 times 1 plus 2. In other words, this is actually true. Here's 110 is replaced with 1 because they're congruent with respect to modulus 9. Now, this is actually a commonly used rule to check if a number in base 10 is divisible by 9 or not. You simply add the individual digits. Okay? So, mod 9 in base 10. So, all the numbers in base 10, since 10 raised to whatever's power is congruent to 1 in mod 9. So when you calculate mod 9, you can just replace this with 1, with 1, with 1. So it becomes, this is because of that, right? So it's congruent to just you add the digit up. So to check if a number is divisible by 9 in base 10, you simply add the individual digits. The sum of digits is going to be the same remainder of the original number. So if number divisible by 9, then a plus b plus c plus d is going to be 0 mod 9. Okay. Now another trick is that if you want to see what is the remainder of this huge number mod 9, are you going to add individual integers here, digits here? You could do that, but there's a quicker way in this case. Why? Because when you think about it, when you take 42 as a number, it may be faster for you. So in other words, here, why? Because this is 42 times 10 to something power plus 43 10 to something power 44. So you don't have to add individual digit. You can just simply add the numbers here. You consider mod 9. However, notice that 45 is a multiple of 9. This is minus 1, this is plus 1. So the pair would cancel, right? 43 is minus 2. Yeah, this is 47 is plus 2. 48 is 45 plus 3. 45 is a multiple of 9. So you know that everything cancels. The whole thing is a multiple of 9. So this is congruent to 0 here, right? So that's a trick you probably want to know. So you don't have to add individual digits. You could do that, but here it is easier to add individual numbers and consider that. Okay. So here is actually in one of the AMC. This is 2017 problem 23 towards the more difficult problems. Here we're saying that we have a big number by putting 1, 2, 3 up to 44 together into a huge number that is 79 digit number. We try to see what is the remainder when n is divided by 45. Now, in order to answer this question, the common trick is that first factor 45, which is 5 and 9, they are relative prime. You consider individual remainder. That's easy to calculate. So what is the remainder when divided by 5 and divided by 9? This is how you're going to solve this problem. Okay, so here 45 equals 5 times 9. So we need to figure out what is the big number n mod 5 and mod 9. So n mod 5, because this is ending with 4. So you know that the remainder is going to be 4, or sometimes it's -1. They're the same thing, right? For the modulus, and the remainder -1 and 4, you can do either way. Now how about 9? Now here we're going to use the trick we just learned. For the 9, you can add the number up. You can add 1 plus 2 plus 3 plus 4 plus 4. Here you plus 43 and 44, right? So it is congruent to the sum of those numbers, right? You don't have to sum individual digits, because if you try to add individual digits, it may be more tedious. You know, like you have 2 digits you don't know how to deal with, right? You could do that, but it's faster to simply add everything up. Okay, so we claim that the remainder is equivalent, is congruent to this number, right? Add up all the digits, but here these 2 digits we added, instead of 4 plus 3, we say 43. Now why this is good? Because you know that this is actually equal 1 plus 44, which is 45, times 44 divided by 2, which is 45 times 22. 45, of course, is a multiple of 9. So in other words, the whole thing is a multiple of 9. So the congruent is 0. Okay. Now, what number, okay, when a number divided by 9 is a multiple, divided by 5, remainder is 4 or -1. You can pretty much, you know, from 1 to 44, you can pretty much figure that number. Okay. That number satisfies both these 2 conditions here. Sorry, is actually 9. Okay, 9 satisfies this. Okay, so the answer And in this case, it's going to be answer C. All right. So let's look at the binary numbers. Binary number meaning digits are only 0 and 1s. Okay. So we need to be able to convert into a binary number to a base 10 number. So this is going to be 1 plus this is going to be 2. This is 0 times 4, and this is going to be 8. In other words, 1 plus 2, which is 3, plus 8, that's going to be 11. All right. So that's going to be 11 here by the definition. Now, it's good to know some commonly used binary numbers. So it's good to know that 10 raised to the 10th power, 2 raised to the 10th power is 1024. Raised to 7th power is 128. Raised to 8th power is 256. Why this is useful? Because it will save you time if you keep this in mind. Okay, for example, a lot of times you're going to see this. Oh, what is this? You're going to count how many zeros we have. 1, 2, 3, 4, 5, 6, 7. 7 0, which is 2 to the 7th power. Of course, 128. And another example is, how do you calculate this, right? If you add everything up, it's going to be very tedious. 1 plus 2 plus 4 plus... There's a better way, which is equal to 1 with a bunch of zeros and then minus 1. Okay, in other words, this is equal to 1 followed by 8 zeros. It's going to be 2 to the 8th power minus 1. That is 255. So this whole thing is 255, right? And what is the max number that can be represented by 6-digit binary number? So if you are told the number is a 6-digit in binary, what is the smallest possible value? That's going to be 1 followed by 5 zeros. How about biggest? It's going to be all ones. 1, 1, 1, 1. 6 ones. Okay. Again, use the same trick. 6 ones equals to 1 with 6 zeros minus 1. In other words, 2 to the 6th power minus 1. That's going to be 63. So that's the answer of those questions. And let's move on. All right. So here another problem is, we are given 3 binary numbers. We try to calculate the product of those numbers mod 8. Now, do you have to calculate that into decimal and then do the multiplication or do a mod 8? The answer is no. There's a quicker way of doing that. Why? Because in binary, we know that 8 is 1, 0, 0. 3 zeros, okay? So when you divide a number by 8, you simply remove the last 3 digits, okay? Just like in the, because this is to the one bunch of zeros, just like in the decimal, in the base 10, if you divide something by 1000, you can just remove the last 3 digits, okay? So in other words, when a number in binary, this is called the floor divide. In other words, you divide by 8, you ignore the fraction, you keep the whole number. Simply truncate the last 3 digits out of it, okay? Now, how to calculate the remainder? The remainder is going to be exactly the final 3 digits, okay? So, in other words, in binary, if a number ending with 0, 0, you know that it's going to be, in this case, z is a multiple of 4. If I have 3 zeros, the number is going to be multiple of 8, right? So that's good to know. Next time when you see a binary number with a bunch of 0 at the end, you know that it's going to be multiple of 2 to the nth power, right? So that's a quicker way of calculating the modulus here. In this case, we can just take the last 3 digits for the x, y, z, okay? So x, y, z, we look at the last 3 digits, which is the remainder, mod 8, right? And then we put them together, yeah, mod 8. And this, again in the binary, this is equal to 1, this is 5, this equal to 7, this equal to 4. Okay, so 5, 7 is also negative 1 in the mod 8, right? And times 4, this is going to be negative 20. Negative 20 is equivalent to what? You add multiple of 8, add 24, it's going to be 4. So final answer is that XYZ mod 8 is 4. Okay, that's about the binary, right? The base 2. Now, another commonly used one is base 16. In base 16, digits is more than 10. It's actually, there is 0 to 15. Of course, we cannot use 1, 5 here. It's going to be confusing. We're going to use A to F, right? So here, this is, base 16. It's going to be 0 to this one. This A is equivalent to 10, okay? So A to F represents 10 to 15 in decimal, all right? And again, for the base 16, it's also good to know the 16th power because the number is going to be multiple of 16th power. So earlier we said that you have to remember 2 to the 8th power is 256. This is actually equal to 16 to the 2nd power. 16 to the 3rd power is going to be 2 to the 12th power. Remember 2 to the 10th power is 1024. So 2 to the 12th power is 4 times of that, which is 4k. Sometimes people say that is 4k, and 4096. Okay, so that's for hex number. Let's look at the real AMC10 problem, base 16. Here, this is 2015. The problem 18 again, towards the more difficult part of the exam. We're saying that base 16, which is sometimes called hexadecimal numbers, are written using the digit 0 to 9 and A to F, right? So among the first 1000 positive integers, there are n whose hexadecimal number contains any numerical digits. In other words, we are interested in all the numbers in hex or in base 16 only has digit 0 to 9. It does not have A to F. Okay? So for example, 13 does not belong there, right? 13 is going to be A to F. But number 9 in base 16 is also 9, right? So that's part of it. We need to find n in order to find the sum of digits of n, right? We need to find how many such numbers are there, all right? Of course, in order to know that, you have to know what is 1000 looks like in hex, right? So that's why it's good to remember 16th power, right? And 16 raised to the 2nd power, 256. Raised to the 3rd power is going to be bigger than 1000. So you know that 1000 is going to be, you want to convert into 16th base. So you're going to decompose as multiple of 16s, right? So in the hex, it's going to be 3e8. Okay, 3e8. Now think about it. All the number from 1 to up to here, and you only want to have in hex numerical digits. You know that it's going to be in hex. How many of them? It's going to be from 0, 1, not from 0, it's going to count from 1 probably, huh? 1, 2, 3, up to 1, up to 399, okay, in hex, because you cannot have numericals, you cannot have A through F, right? So in the hex, we're talking about, in the base 16, those numbers are from 1, 2, up to 399. How many of them? There are 399 of them, right? So this of course, this is in the hex. So here n would equal 399. What is the sum of digit of n? You add it up, it's going to be 21. So the answer is E. Okay, so that's AMC10 on the hex numbers. Let's move on. Okay, here it says what is the greatest possible sum of digits in base 7 representation of a positive number less than 2019. Again, base 7, right? So here you want to check what is the 7 to the second power 49, the third power is 343, fourth power is going to be greater than 2019. Yeah, so you know that 2019 is going to be something here. Now you want maximize the sum of digit. You want a bigger digit. What is the biggest digit in base 7? It's going to be 6. You want a lot of 6, right? And you want the number less than 2019. So the biggest I can get is going to be what? You cannot start with 5. It's going to be 4, 6, 6, 6. That would be the biggest, because you try to use as many 6 as possible in order to have the greatest sum of digits. So try to use bigger digits, in other words 6, and the number is going to be 4, 6, 6, 6. Okay, what is the sum of digits here? You can just add it up, right? So the answer is 22. Okay, that's base 7. Now here we say base 9. Now this, again, the huge number is base 9. What is the remainder when divided by 5? Now you need to consider, what is 9? The meaning everything is a multiple of 9, right? Like 2 plus 5 times 9, and this is going to be 6 times 9 to something power. This is 9, 7 times 9 to some power, 2 times 9 to some power. Notice that 9 and 5 is related, because 9 mod 5 is equal -1, okay, or equal 4, right? So that's important to know. So each digit is D contribute to 9 to the kth power, right? However, 9 mod 5 is 4, and it's easier to use -1, right? So here or here, okay. Or the trick here is that use -1 instead. So which means what? Which means this is 2, this is 5 times -1 raised to the kth power, right? And we're going to use the fact each digit we're depending on the kth position, right? This is 0, right? 9 to the 0th power, 9 to the 1's power, k equal to 1, k equal to 2, k equal to 3, so on and so forth. Okay, so it's really depending on the position of it. So in order to find out all the terms, what you're going to do is you're going to use 2 times -1 to the 0th power plus 5 times -1, right? And you're going to use alternating digit, right? 2 is positive, 5 is negative, positive, negative, positive, negative. So the colored one is negative, the black one is positive. And also for 5, you can just treat it as 0. 6, you can treat it as just because of mod 5, right, is actually 1. 7 is treated as 2. Okay, you do modulus 5. So how do we find out the remainder here? You just add the positive number minus the negative numbers here. So colored digits are at the odd position is going to be -1. Okay, so it's going to be this is number 2 here. Okay, this is the single digit here, and this is negative. Oh, sorry, we come from here. This is number 2 is here, and 5 is 0. We cancel that, and 6 right, is positive, we can treat it as 1. And here we treat it as 2, but it's negative 2, and cancel with this 2. This is 2, right? So this is 2. 5 is equivalent to 0. 6 equivalent to 1. 7 is equivalent to 2, but its color is odd position is negative 2. This is 2. So at the end, it's going to be 3. The answer is D. Okay, that's good to know. It's very important. Okay. In the spring of 2021, there is problem 11, where we saying that we know some base b, we don't know what b is, and we know that this is not divisible by 3. Okay, so notice that here, no matter what b is, b has to be greater than 2, right? B, 3, 4, 6, 7, 8, or greater than 2. And when you do the subtraction, 2, 1 and 2, 1 cancel, you're going to have 0, 0. Remember, one number ending with 0, 0 is going to be multiple of the base raised to something power, b to the nth power, right? So this number is going to be multiple of b to the something power. So if b is multiple of 3, because this has 2 0 at the end, this is going to be at least 3 square multiple. So it cannot be multiple of 3, cannot be multiple of 6, because 6 is also multiple of 3. So you immediately animate this A and C is not possible, right? So in base 10, we use sum of digits, mod 3. Okay, so we need to consider if number divided by 3, right? You know why? In base 10, if you check a number divided by 3, you simply add the digit sum. The reason is very similar to the fact that we check if number divisible by 9. Okay, so here, because 10 mod 3 is also a remainder of 1. So for any digit 10 to the k, when you do mod 3, similar to mod 1, you can just replace this with 1. Okay, d times 1. Okay, but here for 4 and 7, they also mod to 1, right? 4 and 7, yeah. So in other words, in base 4 and base 7 here, you can simply add the digit. Okay, and here notice that 4 and 7, when you add the digit here, 2 to 1, this is 2 to 1. They're the same. So in other words, the remainder of mod 3, right, in base 4 and base 7 here are the same. In other words, the difference would be congruent to 3, right? So 4 and 7 is not going to work. Okay, so the only remaining one is 8. Okay, so in base 4 and 7, we can use the same trick. In other words, to check the number mod 3, you simply add the digits in just like in base 10, base 4, base 7. Okay, that's important to know. So which means what? Which means here and 4 and 7 are not the choices. And here you have 0, 0 is b squared. So we know that multiple of 3 in base 3 and 6. Okay, so the only remaining one is number 8. So base 8, that is true. Okay. Now here is another 2019 problem 18. Again, a little bit difficult here. We have integer k is base k representation of some repeating fraction here. This notation meaning is repeats forever, the 2, 3, 2, 3, 2, 3. The value in decimal in base 10 is going to be 7 over 51. So what is k, right? So notice that when we do the fraction repeating decimals, there's a trick by moving the digit, second places, and in base 10, moving a digit right to the second place is equivalent to multiply the number by 10 to the second power. But in the base k, when you move a decimal digit to 2 places, is equivalent to multiply this number by k squared. Okay, so if I have a number x, if I shift the decimal point by 2 positions, I'm making the number bigger by k squared. K is going to be your base. So in base 10 is equivalent to multiply 100 of it. In base 5 is going to be 25 of it, right? So here we're going to use algebra here, right? So we know that this whole thing, if this whole thing is x, what do we get? We're going to say k squared x is going to be 23.23 repeating itself. This part is x. 23 is not 23. Okay, remember that this is base k. So it's base k. 23 in base k is equivalent to 2k plus 3 in decimal. And x is a fraction that we don't know, right? But we know x is 7 over 15. So you can solve this equation, right? This is decimal here in base 10. You solve for x, right? So this is here. So here you have an equation, and this value x is given, right? So, and then this quadratic equation, factor that, that k is going to be 16. Okay, that's the answer. It's base 16. So the answer is D. Okay, so that's important to know. And this is also, we use the same trick to figure it out in decimal. If someone say, what is the 0.65 repeating? You're going to use the same trick, move the 2 digit in base 10 would be multiply 100, right? So, okay, so that's this base k here is good to know that when your shift digit is equivalent to multiply k squared, and also be careful that some students will make a mistake. You say, oh, this is 23 plus. It's not 23. It's 23 in base k, which is 2k plus 3. Okay, if k equals 10, that's 23. Otherwise, in k equals 16 is not 23. Okay, so that's this problem here. So the answer is D. Move on. It's also good to know the division by 11 in base 10 is checking the sum of odd, sum of even. This is exactly the same argument we know earlier, right? Like when we talk about the modulus, right? So modulus 5 in the base 9, right? So here 11, yeah, 11 here, mod 11, 10 mod 11 is 10 or is negative 1. Okay, so every digit is 10 to the kth power is equivalent to negative 1 to the kth power. So that's why mod 11 is equivalent to the the digit positive negative alternating, right? So use this trick. Now this is another AMC problem, problem 14. Here we say that 19th factorial, which is the multiplication of 1, 2, 3 up to 19, is equal to the huge number here. We try to say TMN, those digits are unknown, right? We try to calculate T plus M plus H. First of all, you know that 19th factorial is going to have a lot of zeros. How many zeros? Just look at how many 5 you have, right? So here you have, in this factorial, you have a lot of 2's powers. You also have 5, 10, and 15. So at least you have 3 zeros. So H, we know for sure is 0. That's good to know. H is 0, okay? But we don't know about T and M. But we're going to use the fact that 19th factorial contains 9. So this whole thing is a multiple of 9. Which means what? Which means sum of digit is multiple of 9. So sum of digit you add it up is going to be something like this. So H is 0. We know that T plus M is going to be in between 0 to 18, right? So the whole thing is here, and so the whole thing could be 3 and 12 in order for the whole value to be multiple of 9s, right? But is it 3 or 12? Yeah. So we need to figure it out because either A or C. Okay. Now we're gonna use the fact that 19 factorial contains 11. So in other words, 11 is also multiple of that. But how to do the 11s? You're gonna do the alternating digit. Okay, use either 1, -1, you know. So here, let's do that. So this one, you know, alternating is going to be, the difference is going to be multiple of 11. So we add it up, it's going to be here, you know, m minus t plus 7, the three possible values, 11, 0, or -1, or m minus t is going to be here. Of course, -18 is impossible because 2-digit cannot be different 18. Both this is possible, but however, given that when they add up to 3 and 12, right? So if 4, so which means this is not possible. So at the add up, it's going to be 12, right? Because the difference is either 4 or 7. When you sum them up, t plus m, it is not possible to be 3. So t plus m equal 12, and then in this case, either the difference is either 4 or -7. -7 is impossible because this is an even number, and the difference must also be an even number. Okay, so the only possible is that the difference is 4, and then you know the digit is 8 and 4. Okay, so the sum is 12. All right, so the answer is C. Another problem here, it says in base 10 2013, again this is from 2013 AMC10, problem 19 is also towards the difficult part of it. So here the last digit is 3. In base 9, however, is like ending with 6. Okay, so here we say that for how many positive integer b, the base b representation has digit 3. In other words, like for in base 10, the digit is 3. How about in base 7, in base 8, in base, you know, different base, right? Let's think about it, right? So here, in any base must be greater than 3. That's for sure, right? Because 3 is a digit. Yeah? Because in base 2, you cannot have digit 3, right? So the base must be at least 4 and up. And also that since in base b, right, base b, the whole number is going to be some multiple of b plus the single digit, which is 3, must equal 2013. And 3 cancels, which means in decimal, you have b must be equal to 2010. Yeah, 2010, when you factor it, is going to be here. So b must be a factor of that. How many factor of this, you know, these 4 prime numbers is going to be 2 times 2 times 2 times 2, right? This will be 16 of them. Okay. However, b cannot be too small, right? So 16 factors, but b cannot be 1, 2, or 3, right? Because 1 is a factor, 2 is also a factor, 3 is a factor, but earlier we said b must be greater than 3. So there must be a total of 13 numbers where could be base. In other words, 2013 in base 5, base 67, base 15, base 10, you know, base 6, you know, all the factors, right? There are 13 factors. Okay, so the answer is C. Okay. So here we say we consider base 10, base 9, and base 11. So basically saying that we're gonna select a 3-digit number in base 10 at random. Okay, we're gonna find the probability that that particular number in base 9 and base 11 are both 3-digit. Right? You know that for 3-digit numbers in base 10, how many of them? What is the range of them? Right? Now we know that it's going to be from the smallest possible. It's going to be 100, 100, and the biggest is going to be 1000 minus 1. Okay, which is 999. Okay, so in base 10, the range is going to be 100 to 999. The total is going to be what? It's going to be 900 of them, right? How about in base 9? So in base 9, it's going to be from 100, base 9, that's equal to 81. Up to 1000, this is the smallest 4-digit. You minus 1 is going to be biggest 3-digit number in base 9. That happens equal to 728. Okay. In base 11, what is the range of 3-digit numbers? In base 11 is going to be this 100 is meaning 11's square is going to be 121. And what is 1000 minus 1? That's going to be here gives you largest 3-digit number. It's 1330. What is a common? Okay, so 3-digit number in all the 3 bases. Okay, so the number must be 121. Yeah, 121, 3-digit here, because 81 is no longer 3-digit, right? This is a 2-digit in base 10, right? So among this range, only the number between 121 to 728 are 3-digit in all bases. Okay, the other number is going to be sometimes 2-digit, sometimes 4-digit here, right? So in other words, we have total this many numbers, but we choose from 3-digit base 10 number, which is 900 of them. The probability would be what? Would be 608 over 900, right? So this is about 2/3, 0.67. 0.6 and 0.7 is going to be more closer to 0.7. The answer is E. Okay, that's the answer. All right. So we reviewed a lot of base K problems. So it's good to know, the multiple of if case is B, the multiple of B's power, and also it's good to know how to check if a number divisible by 9, by 11, and also by 3, right? Also the congruence, right? So there's a common kind of a problem pattern in AMC10. Okay, and thank you for your time. I hope you like the video. Please share and subscribe to the channel.